So before we jump into scattering, I wanted to still cover a little bit, so still mention something about the Black-Scholes equation, which is a question, about an example of how it works. So come up with an okay example. So again, the important thing to know about the Black-Scholes equation is that it describes the price that like a stock option should be. It's an equation of motion for it. And it depends on the stock price, the underlying asset on which you write the option on, which again, an option is a contract to buy or sell the stock at some later date. The stock itself obeys a stochastic differential equation. It's has some rate of return, and then there's some volatility, which is described by a noisy function. And the magnitude of that noisy function is sigma, which is the volatility. And so sigma t is this crazy noisy thing with a function that sort of wiggles around zero and has like an overall magnitude of 1, if you want. The variance of around 0 is 1. So when you multiply by sigma, it sort of describes the kind of standard deviation around 0 that this thing fluctuates around. And notice it's a random function in the rate, so it's the noise here is very significant. It like really modifies the behavior of the stock in a dramatic way. And then what the equation we derived says is that if you have a stock option, which depends on the value of the stock in the time, that this obeys a certain Schrodinger equation that gives you the time evolution of this stock. And the way the boundary condition on this is that there's a special time called the strike time or the expiration date when you have to, that's the time by which you have to exercise this option. So you have to either use the option to buy or sell, or it just expires and then the contract goes away. And so at that time, the strike time, the function looks like this. It's completely as a function of, so this is f of s at time big T as a function of the stock price. So if the stock price is worth more than what you negotiated your option to be at, so this is the strike price. So this is like, you say, I have an option to buy this stock at price S strike up all the way up till time big T. And if I don't exercise the option, if I don't buy the stock before then the option just goes away. So what happens at the end of this time, at the expiration time, the value of the option must be just equal to the difference between the stock price and the negotiated price. Because if the stock price is actually bigger than what you negotiated at, then you'll be gaining this much value by exercising the option, right? Otherwise, if the stock price is less than what you negotiated at, then the option is completely worthless, because you might as well just buy the stock at the lower price than what you negotiated at. You might just throw away the option and just buy the stock, because what's the point of the option if it, you negotiated at a price that's actually higher than the actual stock price at the expiration date, at the expiration time, which is usually its particular time and day. So that's what the function looks like at the late time when it expires. And what the Black-Scholes equation does is it just tells you what the price of a stock option should be at previous times before the expiration date. And that's how the Black-Scholes equation is used. It's used by hedge funds and so-called market makers to figure out what they should sell stock options at. So they want to sell that to people, who want to buy these stock options to, speculate on whether a stock is going to go up or not. And so they want to know what like a fair price is to sell that option at. And so that they use the Black-Scholes equation to estimate what that might be at times before the expiration date. And I'll just write down the equation again, just to emphasize to you how similar it looks to a Schrodinger equation. It's got a single time derivative, just like the Schrodinger equation. Then there's a kind of kinetic energy, which depends on the volatility of the stock. So this is a kind of p-squared term. There's two derivatives with respect to the stock price, which is kind of like our coordinate. Then there's some potential-like terms, which again, little r is related to the risk-free interest rate. And there's this kind of linear derivative term, which you also sometimes see in physical examples where, for instance, we know the derivative operator with respect to coordinates and momentum. So if you have any kind of energy where there's a momentum coupled to something, it might be linear in the momentum, that energy term, then you get something like this. So that's what the equation looks like. And again, the idea is you can use the path integral to solve time-dependent Schrodinger equations like this. And that's what it's used for in finance. But I did want to give you an example of like solving this thing. So the issue, so how does it work? This is your final, it's kind of backwards from a Schrodinger equation. The Schrodinger equation, you start with an initial condition, which you evolve forward in time. But for the Black-Scholes equation, you have a final condition, which is what you sort of based on reasonable assumptions is the sort of final stock option price curve, which is just basic sensibility, right? It's the value of it must be however much more the stock value is above your negotiated price to buy it. So this is for what's called a call option, which is a contract to buy a stock. So this is the final condition. So you have to evolve it backwards in time to see like what happens to that price of the stock option for smaller times. And that's how you can determine what you should sell the stock option at some time before the expiration date. So let's look at that. It's kind of fun to sort of play around with mathematics of this. So here, this data here, I just want to show you some examples of this geometric Brownian motion that describes the stock. And here, the return rate is here 12%. The sigma, the volatility is 0.1, and this is the starting value of the stock. And if you can plot this and see, even with even with a relatively small volatility, here you can make it even 0.01. Now this curve now this is closer to, the black curve is just the average, it's the exponential growth of 12%. But you see, even with such a small variance, there's some likelihood that the curve kind of deviates from the average quite a bit. And if you crank this up, of course, then it can get really crazy, and you get something that doesn't look at all like the average curve. And if you play around with this, and then you look at any stock ticker, actually does a pretty good job of kind of reproducing the overall shapes of things. Here, see this, in this case, the noise drove the stock price way up. So you have that, and then you have, but the Black-Scholes equation is derived right from the stochastic equation, and we saw that it's derived from the idea that you can build a portfolio, which is a collection of stocks and options, such that you eliminate this noise effect. You eliminate all the effects of the random wiggliness. Now, the magnitude of the wiggliness still matters in the Black-Scholes equation. We saw that because that kind of is proportional to that kinetic energy term. But otherwise, this randomness is not part of it. It's a deterministic equation. So we can solve it like we would the Schrodinger equation for the stock option price. So here, the volatility, I set it to 0.1. Here's that 12% return rate. We're assuming we negotiate a price at expiration time, which is expiration time 1 of 100. We're going to negotiate the stock price to be 100. So if the stock is over 100, then we make money at expiration. If it's less, then the stock option isn't worth anything. So that's going to be our boundary condition, right? Either the stock price is worth more than the negotiated price, which is K, I guess. I think I need this. Or otherwise it's not worth anything. And you can solve this way. Do ND solve, it's like solving a Schrodinger equation. It's actually kind of a tricky equation to solve. It's got convergence issues and things like that. But let's compare what happens if the volatility is 0.1 versus volatility is 0.5. A different volatility is what happens to the stock option price. So here it is for the smaller volatility, and this is what generally happens. So when you're close to expiration, right, your curve, the blue, that's the solution, approaches that limiting curve. That's exactly as we'd expect. But before then, at earlier times, of course, the stock option is worth more. And this is what here at 1 year before the expiration. This is what the price curve looks like. This is the value of the stock option given a particular stock value at that time. So this is the stock value as a function of the stock price. So you see it kind of shifts up. It's worth more than what it is worth at expiration, which makes sense because if you have it earlier than the expiration, right, then there's still some time to exercise it and to make some money off of it because the fluctuations might drive the price, above what you negotiated the stock option at, which in this case is 100. So that's the idea. And then what else? We can look at what happens if we have higher volatility. Now, intuitively, if we have higher volatility, then it would mean that presumably the option has more of a chance to kind of work out, right? If you have more volatility, of stock price will fluctuate more, and so there's more of a chance that you're it'll go above your negotiated price. And that's kind of what happens, although there's sort of a limit to it because, of course, it works both ways. The volatility can also drive the stock price significantly down. But as you can see, this is varying the time now. We can see this curve peels off much more from the limiting curve at the expiration time. You see this curve peels off more. So this kind of option is worth more. And generally speaking, according to the Black-Scholes equation, the option value is always a sort of increasing function of the volatility. So the more volatile the stock is, the more the option is worth. And this is what, this kind of thing, or fancier versions of it, which include more effects. That's what this is what's used to by companies to set the price of an option, which they then sell. So yeah, so that's an example of how it works. Hopefully makes a little more sense to you, but I mean, the reason it's related to everything we've been talking about, because, in the end, you're still just solving a Schrodinger equation. And it also, it's kind of interesting. Well, it's a Schrodinger equation in imaginary time, remember, because there's no I partial t, it's just a single partial t. So it's an imaginary time. The other thing to note is that you can actually kind of make sense of this if you recognize that the kind of equation you get, the imaginary time Schrodinger equation, is just a diffusion equation, for those of you who've studied statistical mechanics. And this is kind of like evolving. And the other issue is that the diffusion constant is negative. So it behaves like diffusion backwards in time. So if you think about a function that has a kind of sharp cusp to it, like this limiting function, if you think about evolving it backwards in time, which is sort of like forwards in time for a diffusive process, what should happen is that the function should kind of spread, and it should smooth out all corners, any sharp edges. And that's really what happens with the solution, right? You approach the sharp corner at the expiration date, but for earlier times, you get this smoothed out behavior, and that's what that diffusion term gives you, the volatility. So if I go back here, it's this guy. This is like a diffusion equation is this. And if you put a minus sign in front of the D, that's like diffusion backwards in time, which is what we have here. We have a minus. And of course, this is like a price-dependent diffusion equation, but it's fine. It's sort of the same thing. Again, you can transform this to a regular diffusion by changing variables to log of S. Yeah. So diffusion. Okay, any questions about that? That's sort of the last thing I want to say about it, just to give you an example.
Oh yeah, I have a few questions.
Yeah, great.
So when you said we got our Black-Scholes equation, I think you talked about this a little bit earlier. Is that specifically meant for people who are buying options, or are that meant for the market makers selling the options?
It's for the market. It's the market makers who sell the options using, It's how they can figure out what to set the price, and then of course they want to set it in such a way that it's not exactly at that price, but they want to make some money off of it. But they use the Black-Scholes equation to guide them on what the price should be of the option. And remember, a key feature of the derivation of the Black-Scholes equation is that it's based on this concept of hedging, that you can construct a portfolio where you buy some amount of stock, but then to get rid of the volatility in that stock as it sort of jumps around and changes its value, you also buy some options which kind of go in the opposite direction as the stock price. And so then you can arrange things so that the volatility in your total portfolio, it completely cancels out. And that's also something that hedge funds do, is that they hedge. They buy different amounts of stocks and options in order to eliminate any uncertainty in their position. And that's what actually is responsible for a lot of the strange kind of market behavior that you observe sometimes, like so-called squeezes and things like that. Like if you've heard of gamma squeezes, that's in the news lately. That's just due to the fact that hedge funds and other big entities like that, they hedge their positions so that, and which often results in kind of feedback loops where something happens to the price where they have to hedge more, and it creates a feedback loop where the hedging actually can drive the price of a stock up or down. In the case of a squeeze, it drives it up. But yeah. Yeah.
So I think you showed in here specifically kind of how a call option works. Does this also have like a same principle for like a put option?
Yeah, except the limiting function has a different shape, right? A put option is the option to sell. So let's see. So it's different. The amount you make, I guess, is reversed, right? So you make the difference between the sell value and the current stock price. Because in a put, yeah, so in a put you kind of borrow the stock, and so then you have to when you sell it, you're kind of selling a borrowed stock. So if you sell it at some negotiated price, you have to eventually return that borrowed stock. So then it's like backwards from this. It's linear this way. You want the stock price to be less than the negotiated sell value at expiration. So the limiting curve is different, but the basic principle is still the same, that you have some limiting curve, and then you use the Black-Scholes equation to see how it evolves backwards in time. It'll just evolve differently though, because it has a different final condition. But otherwise it's the same, yeah.
Gotcha. And then I guess I just wanted to quick ask, kind of relating back to the idea of the path integrals that we've been talking about. You said, I think the path integrals we kind of look at here kind of over all the different values a stock could take.
Yeah.
At some point, does that kind of relate to that like Brownian motion simulation that you did, where you kind of simulate a bunch of different noise paths it could take?
Yeah, absolutely. That's right. That's exactly right. So another way of formulating the path integral is but it's the same thing really. It's in terms of the so-called Feynman-Katz formula, and that just tells you that if you have a certain kind of partial differential equation of the Schrodinger type, then a solution to that differential equation to like a Black-Scholes or a Schrodinger equation, that can be written as an expectation value, like an average over a set of stochastic paths. So you can actually formulate the sort of sum over paths that we did for the path integral. You can also just interpret that as an average over many stochastic paths, because the sum over stochastic paths is just another way of summing over all possible paths. You have to be careful with the measure of the path and so on, like how you actually do that, how you do the averaging, but it's the same thing. It's just the equivalent formulation. It's just, we don't normally talk about it because typically in physics grad school, you don't see stochastic processes as a topic. Sometimes it's covered in StatMech, but oftentimes not. So it depends on, if you've seen the Langevin equation, basically, which is this kind of equation where there's a random function in it. If you haven't, then it's sort of not useful to talk about path integrals that way, but that is the way they're talked about in finance, because it's much more natural to think about a sum over a bunch of, or averaging over a bunch of stochastic paths, which are those Brownian motions. But yeah.
Gotcha. Thank you.
Sure. Any more questions? Yeah, I'm only somewhat expert on the stochastic equation stuff. I don't actually, I've never, I'm not a financial advisor. They say I don't know anything about finance, but it's kind of fun to see where you get Schrodinger-like equations in other areas. Similar equations crop up in polymer physics as well, where instead of time, you have the length along the polymer, actually. But yeah. Yeah, so I guess that's it for that. Yeah, anything else? All right, so I'll clear this. Sort of spent more time on it than we normally would, but I think it's kind of fun. So, but now we're back to, I don't want to say boring, but it's sort of more traditional stuff. I guess it's okay. I don't know. Scattering is interesting, of course. And it's important. It's sort of a classic topic in quantum 2 type classes. So we're gonna spend quite a bit of time talking about scattering, but you'll see it's nothing more than application of just the various things we've been talking about already, namely time-dependent perturbation theory, basically, and time-dependent Schrodinger equation. Because what is real scattering if not just a time-dependent problem where you send in a wave packet, it interacts with something, and then it scatters away. And of course, the free particle solutions are very important in this case, because we're kind of assuming that how scattering works is that you're a free particle as you're coming in, there's some interaction, something happens, and then you come out and the scattered particles are also just free particles with some kinetic energy. So that's the basic principle of scattering. And again, we're back now to the book, so now maybe have a little bit more structure if you're reading Bellac. It's chapter 12 in Bellac. So we're kind of back to more traditional topics, I guess. So again, the basic idea of scattering is you have some particle that you're sending in with some wave vector k, and then something happens to it. Maybe it interacts with some target. Something happens. We don't know what. This is like that region 2 in a 1D scattering problem, but we're gonna sort of treat the scattering problem in arbitrary dimensions, and then the particle comes out with some maybe modified wave vector, some modified kinetic energy, modified momentum. And it comes out, and then we have some kind of detector placed out here where we detect the particles along that direction for that particular wave vector k prime. And so we need a few more terms to kind of describe this process. So typically, instead of just a single particle coming in, you typically have more. You have a whole collection of them, whole bunch of them coming in. And so there's some flux associated with that. There's some flux F of particles that are coming in. And again, all of them have momentum h bar k. And usually this flux F, we know it in terms of a particle density, the incoming particle density. And the speed of the particles. So that's the flux in that k direction. And then, of course, there's something that happens in the interaction region. And often it's interacting with some target particles, say. So usually some kind of target in here. And maybe they also have some density, NT. And then when these guys come out, we usually look at them in 3 dimensions in some solid angle, d omega, that's centered around the wave vector direction K prime. So we detect these guys usually in some solid angle. Remember, the solid angle is just 3D notion of angular size. The whole sphere is solid angle 4 pi, and then any fraction of that is just going to be what it is. So what happens? So we can estimate actually the number of scattered particles. The number of scattered particles should in this region in d omega. So it's the number that we detect coming into that solid angle, which we're going to call dn. That's going to be equal to the incoming flux f multiplied by the density of the target multiplied by the solid angle size. And then there's going to be a constant of proportionality that actually gives you the number, and the constant of proportionality is called the differential cross-section. And this is the important thing that we'll need to calculate with quantum mechanics. This is the differential cross section. And let's see, what else can we say about this? Well, what we can also do, of course, is calculate the total number of particles scattered everywhere in the entire, for all the possible values of K prime. And so then the total, of course, would just be the integral of dn, which is just the total number n. And that'll just be the integral over d omega, all the different directions that the scattered particles can go. You integrate over all of them, and you'll get the flux times the target density times sigma, where sigma is the integral d omega d sigma d omega. So, and that gives us what the total cross section is. It's just the integral over all the solid angles of the differential cross section. That's the total cross section. Okay, and we can say more now because we also know about transition rates. And we know that in some sense, what is a scattering? A scattering happens when your particles that are coming in here, this is the initial state, they come in here into the target. They must, in order for them to be scattered, right, they have to change their state. They have to change their momentum and come out with this K prime. So that must mean they undergo some transition between one kind of free particle state and another one, which is, you know, at this wave vector K prime instead. And so there must be some rate of transition for that happening in this process. And we can use the rate as a way of calculating the number of particles that get scattered as well. So not only is this equal to this differential cross-section thing times these factors, which you can view as a sort of definition, but this must also be equal to the number, the target density times the transition rate, gamma, from going from an incoming to an outgoing state, from an initial to a final state for the scattering. And so if this is the overall transition rate, then the kind of amount of that overall rate that goes into a particular solid angle d omega, this must be given by the ratio of d omega over 4 pi, where 4 pi is the total sorry, is the total solid angle. And the idea here is that the density here is necessary because this is the kind of number of times per unit volume that an incoming particle will have an opportunity to make the transition. Because again, the idea is that you have an incoming particle, it interacts with some target that's there at some density. And it transitions with that rate. So the number of attempts per unit volume in that target region that you get to sort of undergo this transition at rate gamma must be, nt. So you can see from this that you can actually get what the differential cross section is in terms of the transition rate. Everything's here identified already, and now we can have a better understanding of what the transition rate is, right? We have here the flux and the differential cross section. That has to be equal to a gamma divided by 4 pi, right? Because everything else is the same in the two equations. You have the solid angle multiplied by the target density. So these two things must be equal to each other, the things in yellow. So from that, we can identify that the differential cross section is equal to the transition rate divided by the flux, right? And the flux, divided by 4 pi, so there's the 4 pi, times the flux, which again, we're gonna write out in terms of what we said it was, which is the initial particle density times the speed, v of the particles. And if you want to do more, we can, of course, we can expand a little bit more. First of all, we can say, well, what is the particle density? Well, we're going to assume that that there's one particle per, it's sort of a dilute beam of particles that's coming in. And so there's one particle per box of size L. So the density here is going to be 1 over L cubed. So we have this 4 pi. So the n just becomes 1 over L cubed. And the speed we can write as the momentum, which is h bar k, divided by m. And this is all multiplied by gamma, the transition rate. So this is a very important formula because you'll be able to use this actually to calculate differential cross sections for using things that you already know. Because, for instance, you can calculate gamma using Fermi's golden rule. This guy. And this is what you'll do on the homework. And you'll know then, once you calculate this, what the differential cross section is for a scattering problem associated with this kind of, with a transition rate gamma. And the transition rate, again, it has to do with the actual details of the process of the incoming particle interacting with the target. But you see there's lots of nice features here. For instance, this L cubed, if you recall, you did on the homework, you calculated Fermi's using Fermi's golden rule. You had, for instance, transition rates to a free particle, which is what you're doing here, that was proportional to the density of states. And you'll see that once you calculate this and you use density of states and you assume, say, the particle is in a periodic box of size L, then you'll get some nice cancellations where eventually these L factors will go away. So that there's nice nice things like that. There's a nice connection to the kinds of things we've already done. And by the way, so what are the final states? So the initial and final states, they're all plane waves. So that's an important point, is that in these problems, the incoming particles and the outgoing ones, they're where we detect them anyway, that's far enough away that there's no potentials acting on them. And so everything here, we're going to assume is sort of described by, plane waves. And again, it's always convenient to put the plane waves in a periodic box. So it's convenient to use the following normalization that, it is a plane wave, e to the I k dot r or k prime. And then for the normalization, you just normalize by L to the 3/2 for a 3-dimensional system, L to the 1/2 for a 1D system, just so when you take, it's so that, when you take the magnitude of psi squared, the phase factor goes away and you integrate over the associated volume of it, then you want to make sure that, you just get L cubed over L cubed, which is 1. So that's a typical normalization used in scattering problems. You just put everything in a periodic or fixed boundary box. It doesn't matter what kind of particular boundary conditions. You always take the box to be large enough that you sort of don't worry about the boundary condition, but it does come up for things like density of states. So then you can get nice cancellations. Whenever you actually write down an answer, like a differential scattering cross-section stuff, that whatever you use to sort of regularize the wave function for these free particle states, that part of it should just drop out of the calculation. So that's another way of just sort of checking to make sure you have it right, is if your answer for something like, the scattering cross-section, if it doesn't depend on what kind of, big box you put your whole system in. So that's the idea. But okay, so that's a little bit, any questions about that? Just the general setup, and we'll do more examples. But this is the first kind of sense of how to connect quantum mechanics to scattering quantities such as the cross-section. But for those of you not familiar with the cross-section or just forgot, it's important for us to talk about just the classical situation. So we'll talk about classical scattering, just to get a better feel of what these quantities are. So for instance, suppose our incoming particle is some large sphere of radius r, and it's coming in at some speed v and hitting a bunch of smaller particles. Here are the targets. Well, if it's moving at speed v, it's going to kind of sweep out a volume, right, as it moves through space here. And the volume it sweeps out is going to be the volume per unit time, right, is going to be v times pi r squared, because that's the cross-sectional area of the sphere as it moves, and as it moves, it'll sweep out its cross-sectional area, which is pi r squared times v per unit time. That's the velocity. So that's the amount of volume it sweeps out, and as it moves through these targets, right, then the number of collisions in here it should be the density of the incoming particles times the density of the target particles times the volume that it sweeps out right? This should give us the number of collisions per unit time as the thing moves through that sea of target particles. Because this is the volume it sweeps out. So that's kind of the amount times NT that'll give us per unit time the amount of volume that is swept out by the incoming particles in the kind of sea of target particles. And that'll give us the total number of target particles that that volume interacts with. And then there's going to be one such volume for each incoming particle that you toss in there. So we multiply by the density of the incoming particles. And that should give us, so let's think about the units again. Units of these two guys, right, is number of particles per unit volume. So the units here are number of particles, there's two volumes, and then there's a volume per unit time. So what this gives us in the end, in terms of units, is something that's number of particles per unit volume per unit time. So that gives us the number of collisions per unit volume per unit time in this kind of setup. And so if we know that by definition this should be equal to, right, the flux times the target density, and let's see what else we had here, times sigma, right? That's the total cross section. And we can also identify the flux in here, right? The flux is what? It's just the incoming particle density times the speed. So this guy is just equal to the flux. So from here, we can identify that this pi r squared must be equal to sigma. That's the only thing remaining. So we see that for this situation, classically, the total cross section is just going to be pi r squared. And it makes sense because what the cross section tells you more or less is kind of the effective area that is seen by the incoming particle. So here, because any target particle that's within that swept out volume that hits that cross section will get, will collide with the incoming particle, then the sort of classical cross section must just be the actual, area of the incoming particle, because any target particle that encounters that area as it sort of is swept out, as it sort of travels along, it'll get scattered. So that's the kind of intuition. And of course, if you had not small particles, but particles of two different sizes, say you had these particles colliding with some other target particles, which might be big, that have some other radius RT, then again, to calculate the cross section, what you would think about is, what is the total area seen by the incoming particle? Well, it's no longer the case that the targets have to be just within the area swept out by, the incoming particle. You can also have like glancing collisions where the incoming particle and the target particle are kind of offset a little bit, right? Like this. And they can be offset by quite a bit, all the way up to when they're just touching each other, right? Where they're just pass through each other, where they're basically just nicking each other like that. So in this case, the classical cross section is going to be the area swept out by the sort of maximal amount of it's basically going to be the area covered by the sum of the two radii, right? Because we can still get a collision even with the two particles barely touching each other. So the cross section here is going to be the sum of the two radii, the incoming and the target squares. So that's the idea. That's the idea of a cross section. It sort of gives you, roughly speaking, the area that the incoming particle sees for purposes of colliding with some target. Okay, any questions about that? So let's talk about differential scattering cross-section a little bit, classically. And a way to do that, a good setup is to think about now. So in this case, we were sort of thinking about big incoming particles and tiny target ones. Here, they're sort of comparable size. You can also think about the opposite situation where you have a big target, right? Where you have a big target and you have a lot of small incoming particles. And in this case, just from the above formula, if the incoming radius is small, then of course, this will be dominated by the total cross section will just be pi times the radius of the target particle squared. But in order to think about which direction the incoming particles go out at, it's worthwhile to think about them coming in at some distance away from the sort of center of mass of the target. Sorry, my tablet's misbehaving a little bit, but okay. So, and that leads us to the notion of an impact parameter. The particle can come in at some distance b. Whoa. Sorry, something up with my tablet. Let me see if I can fix it. Oops. Yeah, so you can have an incoming particle at some distance b away from the midline of the let me see if I can fix this tablet. Hasn't really done this before. But any questions about what we're doing so far? Okay, that's better. I think it was just running out of battery or something. All right, let me clear this. So, all right, imagine a big target. And small incoming particles. And they're going to come in at some distance b above the center of mass of the target. So they'll come in, and imagine these are all sort of hard particles, and it'll be a kind of glancing blow, right? So it'll, if you ever play billiards, right, we know that as it comes out, it'll come out with kind of with the following geometry that if we draw a radius here from the center like that, which will be perpendicular here to the direction along the sphere, then the scattering will occur at equal angles, alpha, away from this surface normal, you could say, from away from the sphere, sort of. And of course, what are we going to do? We're going to look at the scattered particles in some direction theta away from the incoming direction. This is like our direction of the k prime. We're going to look at some direction theta, and these are, of course, parallel lines. Sorry, I didn't draw them very nicely, but these are parallel. It's the direction of the outgoing particle, and that's the direction we're detecting. It's the direction which they're scattered. So we're looking at all the particles that go out in that direction. So these are parallel. Maybe I'll put slash next to them. It means these are parallel. And if they're parallel, then the geometry tells us that this angle must also be alpha, and this angle must also be alpha. And then again, we're looking at angles theta away from the incoming direction. So we see the angles have to add up, and pi is equal to theta plus 2 alpha. So that's the relationship between the sort of scattering angle and the scattered direction, theta. And what else? We know that sine of alpha, that's going to be equal to the impact parameter divided by the radius. And we can see that just from this triangle here, this theta triangle. This theta here, if we think about what this is, this will be the this would be the impact parameter divided by oh, sorry. So this is the radius. Yeah, this is whatever the. So out here, this would be the impact parameter, right? It's where. Let me just indicate impact parameter everywhere. It's here, and it's here, and here. So if I isolate this little triangle, it just looks like this, where theta and then b is at the vertical, and r is the radius of the target particle. So you also have that relationship. And so we can actually write this in terms of the, so we can now connect, right, the impact parameter and the scattering angle. So the impact parameter in the end will be related to theta through this geometry. And the sine of alpha is sine of pi minus theta over 2, which is just cosine of theta over 2. So in the end, we find that the impact parameter is related to the scattered angle like this, just from this geometry. Okay, and why is that useful is because we can now calculate the differential cross section. So since the impact parameter is related to the scattering angle, we can now use the impact parameter as a sort of proxy for the angle and get a differential scattering cross section or as a function of the impact parameter. So what is the differential scattering cross section at a particular impact parameter? Well, if we think about it, if there's a particle at this impact parameter B, then the area that it sees on the target, right, will be everything that's within a kind of rim of size B, right? This is of size B, and this is of thickness dB. So for an impact parameter B, all the incoming particles that live on this rim will have that same impact parameter because that's just a distance away from the center of mass. And the area of that rim is going to be this thickness of the rim, which is the differential element dB, times the circumference of that rim. That's the area of the rim. That's what the effective area that the incoming particle sees on the target. So the differential scattering cross section here is d pi b dB. Just that area swept, the area that the incoming particle sees on the target. But now we can just start plugging in for these various quantities. This is pi r squared sine theta over 2. And we differentiate b here. So that gives us, and we have a b here, so that gives us a cosine theta over 2, right? D theta. So all that happened is the 2's get canceled from the differentiating the dB. And we pick up a sine and cosine. Sine and cosine there. And we can write this as, the other way to write it would be 1/2 pi r squared times d cosine theta. You can use the double angle formula to write it this way. So because this becomes sine theta d theta, and you can use a double angle formula to combine the theta over 2 guys. So what does it mean? It means that we can calculate the differential cross section now, the actual one per solid angle. Why? Because d omega, the solid angle, is going to be 2 pi sine theta d theta, right? That's if you don't care along the phi direction where you are, then that just gives you a factor of 2 pi. And then the differential element, well, it's a little bit, so it's actually, the integral here is like that. So there's a factor of 2 pi for the phi direction, and then if you integrate sine d theta over all the possible values of theta, you just get a factor of 2. So this is 4 pi. So because of this, we can write the sigma d omega as 1 over 2 pi d sigma d cosine theta. Again, because this guy here is just d cosine theta. This is the differential cross section. And we just can figure out what it is. It's already here, right? It must be the 2/2 give me a quarter. The pi's cancel, and you get a quarter r squared. So that's the differential cross section. And it makes some sense, right? Because if we integrate over all the sigmas, we just get the total, uh, we'll get the total cross section, which is what? Sigma d omega, right? It's going to be 4 pi over 4 r squared is pi r squared. And that makes perfect sense. That's like integrating over all the possible impact parameters so that then how much area does the incoming particle see if it can be at any impact parameter? Well, then it'll just see the entire big target sphere, which has a cross-sectional area of pi r squared. So this kind of makes sense. But again, you can use this basic geometry to figure out what it is. So any questions about that? This is just for simple scattering of hard spheres in various limits where you have big initial incoming particles and small targets, or kind of vice versa. When it's vice versa, you can calculate how, what angle the small particles go out based on how far away they are from the midline of the big target particle. And from that, you can calculate the differential cross section, because you can use sort of the impact parameter to relate that to the angle that it goes out. So because the impact parameter is just related to the scattered angle like this. So these are the sort of important formulas for hard sphere scattering. You get the total cross section, get the differential one. And that's it. And it kind of makes sense. This is isotropic, right? It's sort of, it scatters like this in all directions. Right, there's no theta dependence. But when you're working on problems, you typically will have some kind of non-trivial dependence on theta, the outgoing direction. You can have more forward scattering, more backward scattering, right? Then you can have peaks at small theta, or large theta close to pi, things like that. But for this problem, these are sort of simple results. But it's important to have some intuition about it, because once we pull quantum mechanics in, it just becomes a little bit less intuitive, because our quantum mechanical formula for this is not so, I don't know, at least to me, it's not so obvious, right, what these things are. But if you kind of keep in mind the classical version of this, just from hard sphere scattering, if anything hits anything else, then you assume that that's a collision and interaction. Then it becomes a little easier to think about cross sections, because you can just interpret them as the area seen by the incoming particles, and then it's sort of whatever answers you get from the quantum mechanical calculation, you could check, right? If the answer you get in the end, you should get some area, and if it should be at least somewhat related to what your target is, right? So yeah. As we'll see in quantum mechanics, the cross sections are not just simple geometric things, because of essentially wave particle duality. You'll have the interaction process can take place in such a way that it can occur, impact parameters are kind of larger than you would expect. But anyway, we'll get to that. So the next step is to talk about quantum mechanical cross sections and how that works. So we already connected it to a transition rate, which is all you need to do the homework, at least for homework 3. So you have all that. But we're going to do more now. We're going to study the scattering process in more detail. And we know that essentially what, the kinds of problems we'll be worried about is where the target is it's kind of like having a large stationary target, but it's going to be described by some spherically symmetric potential V of R. And that's what really is going to concern us for the most part. We're going to be worried about the solution as it interacts with some region described by a potential, a spherically symmetric potential. And we know that out here, we're going to get incoming plane waves. And it's usually convenient to have them be along the z direction. So there's some normalization and an IKZ. And the z is sort of always in this direction along the incoming direction. So that then really theta, the angle theta, right, it describes the direction of k prime away from the incoming direction. That gives us a nice setup for the spherical coordinates we're going to use. Okay, so I'm out of time, but that's where we'll go on Thursdays. We'll start there and try to develop this problem quantum mechanically so that, you know, we know how to calculate differential cross sections and stuff using Schrodinger equation essentially. But hopefully the classical version of this builds some intuition for the kinds of things you should get. Okay, any questions about that?